Hey guys, welcome to my channel and welcome to another video on AI. So today we'll be going through one of the video recordings from YouTube, and this is from a channel called Why Combinator. Uh, so it's good to learn the know and how of the technology, but it also good to learn from people who invest, people who are going to shape the technology in going forward, and that is where Why Combinator comes into picture. So I just watched one podcast and most of the things that they were talking about in that I know I was able to relate to that. I think they were talking about vertical agents. So even if you're not able to gather much out of the videos, you'll try to understand or listen some of the key words that they talk about it, some of the key technologies or the trends or maybe the pitfalls that we have to be aware of. And this might be similar to the uh, the meetings that you have if you get a chance with the leadership team. They also talk on the same lines, where the money is going, where they want to invest. So some of this is useful if you want to shape up your career and if you want to go ahead in your career, because you cannot be really one dimensional. When I say one dimensional, you cannot really just focus on the technology aspect of it and uh, try to, or maybe think that you will be successful. Yes, you will be successful, but you need to have a longer picture in mind. And this is something that I am enforcing myself to do, and I encourage you to do as well, because I don't had that mindset, but I want to develop a mindset where I try to gather some of the information that some of these leaders talk, because earlier I used to just ignore all of this talk. But I think now, since maybe because I've uh, uh, climbed up the ladder and maybe I'm also part of some of the mid leadership team, that is why I might be interested, or I have shown interest in this. But I would encourage, if even if you are starting out, you're a junior data engineer, or any other post for that matter, it's very important that we understand from the leaders what they are saying, and what topics they are really concerned about, so that we can also learn from them. So with that said, let's look into this. Let's share the screen and we'll watch the video. So we are going to go through a video that is available on YouTube, and this video is recorded by a company called Y Combinator, and as you can see, the short form of the acronym is YC. So as per the definition from Gemini, it says that it's a highly prestigious and influential American technology startup accelerator and VC firm. It was founded in March 2005 by Paul Graham, Jessica, Robert, and Trevor. Since its inception, it has played a pivotal role in launching over 4,000 companies, many of which have become household names in the tech industry. So as you can see that these are the people who actually invest in startups and the other companies. They provide funds to them. And it's very important to get their point of view or an opinion on where this technology is heading, where Gen AI or LLM or any technology related to the recent surge of AI tools is headed. And it's important to go over these videos because that helps you understand what's going on industry wise. Uh, Having the know-how of the technical side of the technology, the pure technical side of the technology is good, but you need to know where the trend is going, what the industry is doing, what the customers are looking for, and even for that matter, what your current organization is doing. And especially when you climb up the ladder and you go into the leadership role, these things become important because you no longer a sole contributor. You have to work in a team environment. You have to get more business for yourself, or for the team rather. So this actually develops overall skills, capabilities of you as a person if you like more challenges. and I can totally relate to it because right now I'm a lead architect, and and that is where I think I am part of a mid leadership team. So we need to make a lot of decisions, and especially I have to be on my toes, or I at least should know various terminologies that are being spoken around, so that I can make a good decision on that. The technologies that I know would be, okay, because I know in and out of those, but AI, Gen AI, especially if somebody comes and asks something on that, I should be able to, get the answer for them or to the team who are approaching me. So let's, let's start the video and we look into this. So we are going to go through this video called Scaling Laws. So let me just click on this.
The deadline to apply for the first YC spring batch is February 11th. If you're accepted, you'll receive $500,000 in investment plus access to the best startup community
So I think they're
in the
starting
world.
with
So apply now and come build the
advertisement.
future with us. Large language models are getting bigger, much bigger. They're also getting smarter. Over the past few years, AI labs have hit on what feels like a winning strategy. Scaling. More parameters, more data, more compute. Keep scaling the models and they keep improving.
Just like Moore's law, we saw the doubling in performance every 18 months. With AI, we have now started to see the doubling every 6 months or so.
But could that be coming to an end? Is the era of scaling finally over? Or are we standing right at the beginning of a brand new scaling paradigm, one that promises to revolutionize AI forever?
So as you can, clearly guess from the intro that the topic for this video is scaling. So usually, or let me do some research. So let me just type in what are various scaling laws in tech. So let's see, what Gemini gives. So in the video, the author was talking about uh, scaling, and you saw a video from Microsoft COE, a snippet of video rather from Microsoft COE, where he was explaining about Moore's law. So scaling law in tech, particularly in the realm of artificial, describes the relationship between a model's performance and the factors like model size. These laws often exhibit. I had only asked about tech, so it has given me, about AIs, but that's okay. Understanding these scaling laws is crucial for researchers and engineers developing and deploying AI models. I think Satya talked about Moore's law. So what is Moore's law of scaling? So let's see what it says. Moore's law, the observation the number of transistors on a microchip doubles approximately every 2 years while the cost of computers is halved. It is not a physical or natural law, but rather a prediction and observation about the semiconductor industry that has held remarkable true for several days. All right. So they were actually the Moore's law is based on the chip, transistor chip, but now more powerful chips have come into play because you need more compute for running those AI models. Okay. Yeah, I think that is all they are explaining. So with the introduction of Gen AI, and especially the powerful chips around it, especially developed by NVIDIA, this law might not be, true anymore.
In November of 2019, OpenAI released GPT-2, its largest ever model with 1.5 billion parameters. The next summer, they released its successor, GPT-3, which was something we'd never seen before. Not only was GPT-3 far more useful and usable, it was also much bigger, over 100 times bigger than GPT-2. The era of scaling laws had arrived.
See, there are two important things here. One is the parameters and the token size. I think token size may be referring to the amount of input information that we can feed into a model, whereas parameters is something complex. So let me just try to get both the definition. What is token size? So let's see what it returns. Particularly with large token refers to a chunk of we understand what is token. Give me what is token size, token limit, number of tokens that they can process. This is the context window. Yes. Input that we provide by token understanding large. Okay. So token size, our understanding of token size is fine, that it is the amount of text that the LLM models can process one at a time, or in simple words, whatever I'm typing in here in this box, there could be a limit to it. So that is our token size. And the second part was, what are parameters with respect to LLM model? So let's see what it returns. In the context of the parameter, the values that the model learns during its training process, these parameters essentially the building blocks of the model's knowledge, and they're used for capture patterns and relationships between data, make predictions, and generate text analogy. Imagine a vast. So this is the thing that I like about Gemini, guys. So they give you this analogy. Imagine a vast network of interconnected knobs and dials. Each knob or dial represents parameter. Imagine a vast network of interconnected knobs and dials. Each knob or dial represents a parameter in LLM training. That knobs. Okay, so the larger the network, the better the inference, or the better the output of LLM model is. Numerous LLMs have millions, billions of intelligence. The more parameter, the complex pattern the model can capture, learn from data. Parameters are not finally, but they are learned. Okay, so once you train a model, that is where the parameters are generated, stored as numbers. Parameter typically stored as large arrays of numbers, weights, and biases. Model capacity, understanding the role of parameters. Okay, so we loosely understand what parameters is. It's the larger the parameter size, the more bigger the LLM model is.
Before GPT-3, LLMs were already getting bigger, but it was still anyone's guess whether or not that extra size, data, and compute would be worth it. There was no guarantee that making your model 100 times bigger would also make it 100 times better. What if they started to run into diminishing returns? It wasn't until January of 2020 when Jared Kaplan, Sam McCandlish, and their colleagues at OpenAI released the influential Scaling Laws for Neural Language Models paper, that the field started to take notice. Think of training AI models like a recipe. You have three main ingredients: the model itself, the data it's trained on, and the compute power used to train it. Larger models have more parameters. These are the internal values of the neural net that are tweaked and trained in order to make predictions. These models are also typically trained on much more data, measured in tokens, which for LLMs are often words or parts of words. Finally, training these larger models requires computing power, which means more GPUs running for longer, using more and more energy. What the Scaling Laws paper revealed was that by cranking up all three, the parameters, the data, and the compute, the result was a smooth, consistent improvement in model performance in the form of a power law. Performance, it turned out, depends much more on scale than on the algorithm. Later in the year, more research from OpenAI confirmed that these scaling laws worked for other kinds of models too. On text-to-image, image-to-text, and even math, the same scaling laws were there. But back in early 2020, LLM scaling laws were pretty much unknown outside of OpenAI. That is, except for one person. The anonymous researcher and writer, Gwern, was one of the first people to hone in on what he called the scaling hypothesis. Scale up the size, the data, and the compute, and watch intelligence emerge.
Maybe intelligence really is just like a lot of compute applied to a lot of data, applied to a lot of parameters. Maybe Moravec and Legge and Kurzweil were right.
Gwern's post brought scaling laws into the mainstream. And over time, what started as a quiet observation quickly turned into a foundational principle for AI development. But OpenAI's research was just a part of the picture. In 2022, Google DeepMind released their own research on scaling laws, and they added an important missing piece. It turned out that it's not just about making models bigger, it's also about making sure you train them on enough data. Researchers were looking to find the most optimal model size and training data for a given compute budget. So they trained over 400 models of different sizes with different amounts of data. And what they found was surprising. Their research suggested that previous LLMs like GPT-3 were actually undertrained. These models were huge, but they hadn't been trained on enough text to fully realize their potential. To test this, they trained Chinchilla, an LLM less than half the size of GPT-3, but with 4 times more data. And it won. Chinchilla was far better than models double, even triple its size. These so-called Chinchilla scaling laws meant that training the optimal model wasn't just about making the model larger, but also about having enough data to feed it. Chinchilla was a huge milestone on the road to training the frontier AI models we have today, like GPT-4o, Claude 3.5 Sonnet, and others. Labs learned they could trust in the scaling laws and get reliably better and better models. So the future of AI is just bigger and bigger models forever, right? Well, recently there's been plenty of debate within the AI community about whether or not we've finally reached the limit.
I think what the crux of the video up till now, since we last interrupted, was that not only the GPU or the parameters, it's also depends on the data that your model is trained on. So you can have a smaller model that is trained on a good amount of data and good quality of data as well as amount of data can beat a large model rather, which is trained on maybe junk data, even though the data volume is high. So the data volume also is a key factor in determining how better the performance of the data of the model is. And yeah, I think that is what is being talked about if you just try to generalize it.
Of scaling laws. Some argued that as the latest generation of models have gotten bigger and more expensive, capabilities have started to plateau.
There's a lot of debate. In fact, just in the last multiple weeks, though, have we hit the wall with scaling laws?
The current generation of LLM models are roughly, few companies have converged at the top, but I think they're all working on our next versions too.
We're increasing GPUs at the same rate, but we're not getting the intelligence improvements at all.
Meanwhile, rumors have leaked out of major labs about failed training runs and diminishing returns. Others have speculated that the lack of high-quality data to train new models has also become a major bottleneck.
One practical issue we could have is we could run out of data. For various reasons, I think that's not going to happen. But, if you look at it very, very naively, we're not that far from running out of data. And so it's like we just don't have the data to continue the scaling curves.
So, if the old scaling laws are beginning to lose their edge, what comes next? What if there were a new frontier for scaling from a brand new kind of model? OpenAI's new class of reasoning models hints at a potential new direction.
So, reasoning models are a new class of models where we would expect the models to, do some research on our behalf. So up till now, if we have to generalize any LLM model, which are not, classified as reasoning models, they are just essentially completing the sentences, nothing more than that. But these models, I've not gone into deep into it. I think there is O1 series or O series rather for the models that are called reasoning models, but let's look into it.
In a previous video, we explained how O1 learns to think through complex problems using its own chain of thought. And OpenAI researchers found that the longer O1 was able to think, the better it performed. It wasn't immediately clear how well this strategy would continue to scale up, but now with
so chain of thought, that's an important thing. So how these models, O models are able to do the reasoning. So maybe that is where we need to ask what is chain of thought in reasoning models. Reasoning is a technique used to improve the reasoning abilities of large language models. It essentially guides the model to break down the complex problem into a series of intermediate steps, mimicking the way humans think. This approach helps LLMs to solve tasks that require logical deduction and multiple step reasoning more efficiently. Instead of directly asking them for final, the prompt is designed to encourage the model to generate a series of intermediate reasoning steps. Then it's a chain of thoughts that lead to final answer. So maybe this can be viewed as, the LLMs, instead of getting the answer straight away, they divide the task and, get the answer. Zero shot leverage knowledge within LLMs tackle problem within few short manual short automatic benefits of chain of thought, complex reasoning. And although this topic requires, detailed research, but essentially, I think once you write the prompt, I think how it would work is once you write the prompt, you will not get the answer immediately. It would have to think on its own. Maybe, divide whatever we are asking into multiple, tasks. Unlike agents which actually, try to maybe access external systems or external tools, this is something that goes on within LLM. So it will LLM somehow internally would break down the problem and then try to find the answer for each of the problem and then give you the final answer.
With the recent release of its successor, O3, the sky seems to be the limit for this new paradigm of scaling LLMs. O3 made headlines when it was announced, as it smashed benchmarks that were previously considered far out of reach for AI. From software engineering to math to PhD level science questions, O3 easily surpasses the old state-of-the-art results. O3 isn't just a small improvement on its predecessors, it's a huge leap. And OpenAI researchers say they have every reason to believe this trajectory will continue. It may even be on a path to artificial general intelligence. Instead of continuing to scale up the model size during training, it seems likely that researchers will shift focus to scaling the amount of compute available to the model for its chain of thought, also called test time compute. By letting models think for longer, LLMs like O1 and O3 can leverage more compute on the fly, scaling up their intelligence when it's needed for harder and harder problems. Scaling pre-training may have plateaued, but by training test time compute, OpenAI may have just opened up an entirely new paradigm for scaling laws, potentially unlocking capabilities we never thought possible. Large language models are a key piece of the hunt to artificial general intelligence. These same principles of scaling appear to hold for other models too: image diffusion models, protein folding, and chemical models, even world models for robotics, like for self-driving. One thing is clear. It might be mid-game for large language models, but we are clearly still in the early game for scaling other modalities. Buckle up.
Okay. So I think at the end, what the host is talking about, I think host is Gary Tan. What he's talking about is that there could be new way of scaling, especially with the rise of reasoning models. So I'm not exactly sure how reasoning model works, but I think he was referring to a term called test time compute. So maybe once you write the prompt, because the model has to think on its own, it would be using some GPUs. So this is different from your pre-trained model, where you've already used the massive amount of compute because of the massive amount of data. Maybe it's worth checking what is test time compute. Let me see. What a test time compute is a buzzing field in the eye that focuses on enhancing the performance during inference stage, which is when the model actually used to generate output like. So it's like it is doing in runtime. So if you try to compare it with the traditional way of developing the apps, it's like it's thinking or taking more of the GPUs during the runtime, which is interesting. So I think for now this would be all. And if you got something out of the video, please subscribe to this channel and try to spread it out as much as you can. So we are actually learning together. There is nothing, no secret, no hiding behind it. I'm not an expert. So by making a habit of learning together, we will eventually maybe become somehow, uh, you know, not expert, maybe people, who can work with the technology, try to find the answers from where it could be found. And more importantly, we'll be able to understand the terminologies that is being spoken around. So thank you guys. Thank you for joining, and we'll see you in the next video. Bye, guys.